In today's lesson, we'll be taking a look at probing, which is an advanced technique to set up tool and work offsets in the machine. We'll be using the Haas Visual Quick Code, or VQC for short. VQC is a set of easy-to-use graphical templates for probing. We'll start with tool probing, and then move on to work probing later in the video. Before we begin, we need to discuss some limitations of the probing system. Most probing routines are designed for relatively small diameter tools only, less than 3/4 of an inch. Using a tool such as a face mill during automated probing can lead to catastrophic results, including crashing the machine, destroying the tool probe, and causing thousands of dollars in damage. Check with your instructor or shop supervisor before probing any new tools or before running any new probing routines that you haven't used before. We'll begin by looking at the auto-length-only probing routine. Press the MDI key. Press the Program key in the display group to activate the tabs at the top of the screen. Use the cursor arrows to move over to the VQC tab. Cursor down and press Enter to select the tool probing templates. There are 7 different tool probing templates shown. Each picture represents a different tool probing template. Notice the red selection box around the first picture. This tool probing routine is for auto length only. Let's try this one first. In the top right of the screen, it's asking us to enter the tool number, which in our case will be number 2. We can select a program to insert this probing routine into. We can output to the current program active in memory. We can output to MDI, or we can create a program to put this code into. By far, the most frequently used option is number 3, output to MDI. Putting the code into MDI makes it easy to use for the setup process, and we no longer need the code after probing is complete. Press MDI to activate the MDI panel on the display. The panel is active when it has a white background color. Verify the code in the MDI window is correct before pressing Cycle Start to run the probing routine. After verifying the code, press Cycle Start. The machine will change to the commanded tool, then move the table so the tool probe is under the spindle. The spindle will slowly lower and the tool will contact the probe. Keep a hand on the Feed Hold button to stop the machine if something doesn't seem right. After the 3rd automatic touch, the probing cycle is complete. Now, let's try the auto length and diameter routine. Again, we go to MDI, press Program to activate the VQC tab, and go down to Tool Setting. Find the template with the name Auto Length and Diameter. Many of the pictures look alike, so it's important to read the name in yellow text. This is the one. There are 3 questions to answer. We start with the tool number. We'll enter Tool 2. Now, we need to get the approximate length of the tool. A tape measure or machinist scale will easily get us within 1/4 inch, which is close enough for this value. Note, this dimension is measured from the spindle nose to the bottom of the tool and includes the tool holder flange. Enter the tool length. The length you enter will be different for every tool. Now, we'll enter the tool diameter. This number needs to be very close to the tool's actual diameter. It is not an estimate or a guess. Again, we'll choose option 3, output to MDI. Press MDI. Ensure the code has proper parameters you intend to use, including the tool number, length, and diameter. The tool will move toward the probe, pause slightly above it, then start spinning counterclockwise. The reverse direction of rotation is what allows the tool to touch the probe while spinning without damaging either one. It will touch a few times for length. The tool will then move over and down a short distance to check the diameter. It will touch on both sides of the probe. The routine is now complete, but we're not quite done yet. We need to go into the offsets table to check the diameter value. This is the actual measured rotating diameter from the probing process. It's not very common to use the full measured value of the diameter. We'll make a note of the difference compared to the tool's nominal diameter, then we'll enter that difference into the diameter wear column on the tool offset table. This number is typically a rather small value. Now, let's go back to the diameter column and zero out that value. Type 0, then press F1 to insert 0 as the value. We get a warning saying this change in offsets is greater than setting 142. Setting 142 is the maximum allowable change to offsets. It's really just making sure we meant to make that change. Press Y for yes. The diameter is now zeroed out. Warning: do not leave tool diameter offset values in the control if you do not intend to make use of them. Doing so can lead to unintended results when running programs, including the potential for broken tools. Now, let's look at the auto-length sequential tools routine. This one is commonly used when setting up for a new production run, so long as your tools are relatively small diameter and in sequential order. Again, the pictures look alike, so be sure to read the name of the routine. Enter the first tool number and last tool number just as numerals without the letter T. To output to MDI, we can simply press 3 to select that option. Press MDI and verify your input parameters for this probing routine, including the numbers of the first and last tools. Ensure a tool is present in each location in the sequence. An empty tool position during probing can cause the machine to crash, resulting in thousands of dollars in damage. Also ensure there are no face mills in any position, including between the first and last tool numbers. The auto-length sequential tools routine cannot be used with face mills, and if it is, will result in serious and costly damage to the probe. The machine will switch to the first tool in the sequence, then begin the probing routine. After probing the first tool, the machine will automatically switch to the next tool and begin probing it. The machine will repeat the process for each tool in the sequence. The sequential probing is now complete. If the tools are not in sequential order, we can use the auto-length only random tools routine. Select the auto-length only random tools routine from the available VQC templates. Today, we'll be probing tools 6, 4, and 2 in that order. Input each tool number, one at a time, pressing Enter after each. The remaining questions each need to be answered with a 0 input to avoid probing any additional tools. Again, select Option 3 to output the code to the MDI window. Select MDI mode and verify the correct probing template parameters in the MDI window. Ensure there are no face mills in any tool position called in the probing routine. Still in MDI mode, press Cycle Start to initiate the probing sequence. Notice the machine switched to tool 6, the first in our random order probing sequence. Next, the machine will probe tool 4. And finally, tool number 2. With the final beep, the probing sequence is complete. Now let's take a look at probing a face mill. Select the manual length only routine with a graphic of a face mill. Note the instructions in yellow to handle jog the machine such that one flute is approximately 0.4 inches above the optical tool setter. Before running the routine, we must manually handle jog the machine into position. Use caution to avoid vices and work holding fixtures when jogging the Z-axis downward with the large face mill tool. Furthermore, slow the jog rate and use caution while approaching the tool setter. At no point should the tool ever contact the setter while jogging. With the tool close to the height setter, switch to a slower 1/1000th jog rate. Then, lean into the machine for a close look at the position of the tool in relation to the height setter. You may need to orient the tool slightly by hand to place one carbide insert above the touchpad. Here's a closer look from another angle. Notice we've jogged the machine such that the carbide insert is directly above the height setter touchpad. We're ready to begin the probing routine. The probing routine is now complete. That concludes the basic tool probing operations. Now, let's take a look at work setup using the spindle probe. We'll begin with the probe vice corner routine. Back in MDI mode, press Program to activate the VQC tab. Select Spindle Probing 1 through 9. Select the routine with the name Probe Vice Corner. Although it says Vice Corner, this routine is more frequently used to probe the stock material workpiece. Here, we see a top view of the operation. Note the yellow instructions to handle jog the probe over the back left corner of the workpiece. Let's make those moves now. Use caution while jogging downward toward the workpiece. Select the slower 1/1000th jog increment when the probe is near the workpiece. We're now in position. Let's go back to our probing template. We have a few questions to answer. First, enter the work offset. Here, we're using G54, so we enter just 54. We now need to measure the approximate dimensions of our workpiece within a 1/4 inch. A tape measure is a suitable device for this step. We measure 4 inches in the X by 1.5 inches in the Y. Enter those values into the VQC template, ensuring a decimal point after whole numbers. For Z-depth, this is not the depth of the workpiece. Rather, this is how far down the probe will move. Never enter more than -0.75 Z-depth when probing without checking with your instructor or shop supervisor. Entering too great of a probing depth can cause the probe body to crash into the workpiece, resulting in severe and expensive damage to the probe. In our case, as in many cases, a probe depth of 0.6 works well. Output the code to MDI by choosing option 3. Check the parameters and run the routine. Here's the routine running. Notice, the probe first moves to the center of the block, then probes the Z surface. It then probes the center of each side and returns above the corner. When probing is complete, jog upward in Z or command a tool change. Now, let's look at the routine probe center of block, start from center. Along with the work offset number, we need to enter the X and Y dimensions of the block, as well as the Z depth for our probing operation. Also note, in this routine the probe should be jogged to approximately 0.4 inches above the center of the block. Again, we'll use -0.6 for our Z depth. Before running the probing routine, let's jog into position. We'll move the Z-axis so the probe stylus is about 0.4 inches above the stock material surface. We'll double-check our probing parameters and run the routine. The routine probes the Z surface of the block first, then touches each of the 4 sides to determine the exact width of the block in the X and Y directions before returning to the center point. The probing operation is now complete. Another common way to establish the work origin is by using the probe external corner routine. This routine is located on the second page of VQC templates in the Spindle Probe 10 through 18 section. Note, this routine is different from the probe vice corner routine. In this routine, the probe must start below the surface and away from the sides of the workpiece. Also, you have your choice of probing the 4 different corners. Also note, the distances shown are not the width and depth of the block, but rather the distance between probing points. The initial lead-in distance from the corner is fixed at approximately 1/2 inch. You will set the distance from the first probing point to the second for the X and Y directions. For this part, we'll set the X distance between probing points to 3 inches. We'll set the distance between probing points on the Y-axis to 1 inch. These numbers will vary depending upon the part. We'll select corner number 3 for the work origin for this job and output the code to the MDI window. After checking our inputs, we'll take a look in the machine and notice we have not yet moved the probe into the correct position to begin this routine. We can go back into VQC to reference the visual graphic. Notice, the probe needs to be moved away from the corner so that it will not contact the sides when moving parallel to them. Let's jog into position. Now that we're in position, we can run the probing routine. Notice the second touch misses the side and just barely touches the corner. Our distance between probing points in the Y direction was too large. This is a problem we need to fix. Probing on the other side looks good. So, let's quickly redo that routine, changing the Y distance between probing points to be 0.75 rather than the 1 inch we used before. That looks much better. Note, the probe external corner routine does not include Z-surface probing. After running the probe external corner routine, the Z-surface must be probed separately. Let's take a look at that process. First, we'll jog the machine into position about 4/10 of an inch above the surface. Then, from our VQC templates, we'll select the Probe Z Surface routine. Enter the work offsets such as 54 and output to MDI. Verify the code and we're ready to run. After 2 touches, the Probe Z Surface routine is complete. Sometimes we need to find the center of a round part. For this, we'll use the Probe Boss routine. First, we need the approximate diameter of our round workpiece. In our case, it's 3.5 inches. Handle jog the machine so the workpiece is directly below the spindle probe. Jog the Z-axis down using caution while approaching the workpiece. Make any X and Y adjustments necessary to get the workpiece approximately centered beneath the probe. On the second page of VQC templates, choose the routine called Probe Boss. Enter the work coordinates such as 54. Enter the workpiece diameter, and then the Z-depth. The Z-depth is not the thickness of the workpiece. It is the distance the probe should move downward to contact the side of the workpiece. Never enter a Z-depth deeper than -0.75 inches without checking with your instructor or shop supervisor. We output to MDI, check our input parameters, and we're ready to go. The machine will probe at 4 points around the cylinder, with 2 touches at each point to accurately establish the position. The center of the cylinder is now set as the work coordinate origin. Note, the Probe Boss routine does not probe the Z-surface. We need to probe the Z-surface separately. Be sure to use the same work offset number used previously, in our case, 54. This concludes the basic spindle probing operations. Now, let's switch to a different tool to verify the position of our work coordinates. We can enter the following codes into the MDI window: G00, G90, G54, X0, Y0. G00 means rapid traverse. travel at the maximum speed possible. G90 means use absolute positioning, one fixed origin. G54 means apply the work coordinate system number 1. Right now, we have it set as the corner of the block. X0, Y0 means move to the origin. Be sure you do not enter any Z moves in this code, or a machine crash may result. First, we'll jog the tool into position above the workpiece. Now, let's enter those codes in MDI mode. We need to clear out the prior code from probing, so we press the Erase Program key. We then enter G0, G90, G54, X0, Y0. No spaces are necessary. To transfer the code from the input line to the MDI window, press the Enter key. Here are those codes one more time: G0, G90, G54, X0, Y0. Before running that code in MDI, ensure the tool is well above the workpiece. Press Cycle Start. Here's that again from another angle. Now, let's visually verify our Z work offset and tool height offsets in conjunction. First, jog the machine so the tool is well off the side of the workpiece and will not contact the workpiece when moving down. Next, ensure the machine is set to 5% rapid override. Any errors in the setup process or in the following code can result in a severe machine crash. Clear any existing codes from the MDI window and write the following 2 lines of code: G00, G90, G54. This line of code sets the machine to move with rapid positioning using absolute coordinates while referencing the work coordinate system number 1, known as G54. The next line of code is G43, H04, Z0. G43 applies tool length compensation. The H number must match the T number in most circumstances. Depending on how setting 15 is configured in your machine control, the machine may or may not alarm out if the H number does not match the currently active tool. It is always the operator's responsibility to ensure proper height offset H numbers are called. The Z0 move commands the machine to move to the Z0 position, where the bottom of the tool is at the same plane as the top of the workpiece. This move takes place with rapid motion, as fast as the machine can move, due to the G00 modal command on the previous line of code. For this reason, double-check that the rapid traverse is set to 5% override. With the tool clear of the workpiece, rapid set at 5%, and our thumb ready to press Feed Hold, go ahead and press Cycle Start. Be sure to hold if the tool moves below the expected level, in our case, the top of the workpiece. Jog sideways closer to the workpiece to visually verify that the bottom of the tool is indeed at the same height as the top of the workpiece. Here's a closer view. Our Z height offset looks correct. We have now completed visually verifying our Z work offset and one of our tool offsets. This process can be repeated for each tool, while being sure to change the H number in the MDI code to match the number of the active tool. After watching this video, you may feel pretty confident to begin. However, due to the fragile and expensive nature of tools, CNC machinery, and especially probing equipment, check with your instructor or shop supervisor before running any probing routines or MDI codes for the first few times. Finally, remember that at any time on a machine, if something doesn't look right or sound right, even during probing, you can always press the emergency stop to bring all motion to a halt. With careful preparation and practice, the probe system can be an efficient and accurate way to set up almost any job. Thanks for watching, and we'll see you in the next video.